conditions actually to be able to actually achieve state feedback linearizability. And I'm not proving the whole thing. It's a bit hard for me at the moment to do that actually. I don't think I have to think actually if I can do this actually, but it would possibly kick pretty much over the whole actually frame of this whole lecture. But there is a gentleman who has pretty much published actually in that area. There is a book, actually there's some well-established books. I possibly would personally start looking into a book by Khalil, because there actually things are quite well explained. And then actually in the next step I would possibly go into a book by Isidori. Isidori is not on the list, the book by Khalil is on the list.
A typed book, right? Very old book.
The Khalil's book gets always published again because it's so brilliant. That's my personal opinion. But yes, we are now past. I think we are recording things here already. But oh no, sorry, Khalil.
Yes.
But I will explain this in a minute again. Yeah. Right. Good. Oi. Right. Can we see? It's interesting. Good morning. Morning. Early morning. Yes, thank you for coming. Actually, it's yes, we don't want to look at this one here at the moment. We will look at this later. I prepared this only actually. Let me, because I want to be sure that it works. MATLAB simulation. Apart from that, yes, again 3 hours. Brought my own material. Yesterday actually we spoke about feedback linearization. Yes, and I do appreciate it's early. We spoke about feedback linearization, that actually, I must admit, is quite a bit of a tough topic actually in general. It's not trivial. But I think actually, as I said, the first steps actually, I think they were quite actually digestible. The problem obviously is that we have to learn a lot of new notation. Can anyone actually possibly just give me a glimpse of an idea actually, what is feedback linearization? We just go through it actually for a minute and maybe, what kind of concepts did we look at? Do you have a good idea actually? Who wants to say something? And don't worry a bit about actually saying something wrong. It doesn't matter actually. I just simply understand actually where we are. That's what it is. I can't repeat the whole thing because I need to carry on with material. But I just simply want to actually just put things back in mind. Feedback linearization. Any cool idea? Where are we with that? What did we had some nonlinear affine system, isn't it? That's what it was. We had this kind of system there. And what did we try to do?
To use the control inputs U to linearize nonlinear systems and then gather
Yeah, is a fair summary. So I mean, that's a broad summary actually, and I would say yes, it's correct. Specifically, we were looking obviously in terms actually of, at first obviously in terms of a specific output, y, isn't it? And yes, we were obviously trying to use actually u here to create obviously a controller so that we have a new input, and through that new input actually we can create actually an overall linear input-output behavior. Yeah? So it's pretty much actually through, at first, just an, well, not arbitrarily chosen. I mean, people don't arbitrarily choose actually measurement outputs, but or actually certain controlled outputs. I mean, this is a certain controlled output, while actually U is obviously our control signal. Right. And so from that point of view, we had obviously in the beginning that strange kind of step. And yeah, I'm just trying to bring things back. I mean, we will use it today, actually, just in the beginning of our lecture set, but I'm trying to bring it back to you actually, so that actually maybe you're pretty much obviously having some idea. So, what did we do actually with y? What did we do with y? Sorry? We took the time derivative, isn't it? And what do we want to achieve by doing so? Yes, so yeah, so find actually some form of relationship between input and output. Yes, that's correct. So and well, what's that relationship? I mean, how do we actually assess that kind of a relationship? Actually, what do we do actually? I know we're. Yeah, we use the Lie derivative, or Lie derivative. As a German, I don't even know how to pronounce these things. What do we want to find actually, in particular, actually through these Lie derivatives?
The relative degree.
We want to find the relative degree actually of the system in relation to our output. Yeah? So what we do effectively is here actually y dot equals dh dx. That gives us x dot dh dx. And then we can replace this, and we've seen this yesterday, and you don't need to, in that sense, actually rewrite this or so. So we do this. We get obviously these two terms once we multiply this out. So which part actually of this equation is now important to understand actually what the relative degree is here?
The second part.
The second one, isn't it? Yes. So we have here our LFH, which is obviously the kind of notation actually we have, LGH. And what we want is effectively, well, I mean, if this was now relative degree 1, what would happen here? Yes, should be non-zero. And I've done something, or I haven't done something. I haven't switched off the sound of my mobile phone, so if you can do that yourself, I won't be called now because I switched off the ringing tone. My apologies. So we want this non-zero. So if this here is non-zero, then actually rho equals 1. So but if this is 0, then we know effectively dh dx f of x, and this thing is gone there, and we have this one there. So but then actually we can get the second derivative and just simply continue. So that's what it is. So actually this is, as we said, LFH, so we get here in that sense we get d LFH dx times f of x plus d LFH dx gx u. And so the next test would be obviously then, is it 0? If it's not 0, hey, then this is rho equals 2. And if it's 0, then we just continue. Yeah? But once it is non-zero, well, what can we do then? Once we have that relative degree found, what can we do?
Find the input u.
Yes, so we can actually find the input u, we can cancel for the nonlinearities which are affecting pretty much our derivative of y. Yeah? So that's done actually that step. So effectively, for instance, here, if rho was equals 2, then actually we would have here the LGF H not equals 0, and we could actually write this then obviously in that format. So we have here minus LF H yeah, plus V, and then we have here LG LF H as an example. So well, the dilemma of that, or what was the dilemma of this, or what was the problem actually, if actually with the relative degree in relation actually to the system order?
You cannot be sure that it will be stable for the specific output that you're using, because the only stable is the relative degree is equal
It's essentially
to number of state variables.
yes, yes, exactly. So we want to have rho equals being actually the number actually of states actually in the whole system. Yeah? Because I mean, if not actually, then we saw actually there were these extra dynamics left. For instance, in the special example there actually, this example here, we had a bit of a problem. Obviously, the relative degree here is 1. And if we just cancel this, then we in principle don't really know what's happening here. We could analyze this actually, but these are the so-called zero dynamics, and they can be actually a bit of a trouble. In that sense, actually, the aim is pretty much actually to find actually, or to have in principle the relative degree equals actually the system order, but not every output actually can achieve that. Yeah? That was the problem. So hence, what did we introduce? Sorry? We introduced Lie brackets, and we tried to see actually if we can use these Lie brackets to achieve state feedback linearization. Yeah? So effectively, so that actually rho equals n, And we wanted to introduce pretty much some form of test, or actually some form of analysis, which tells us that we can find a very specific output which guarantees us actually that rho equals actually the system order n. Yeah? So we want to, in the next step, we wanted to design actually an output H, so that actually we can create actually a relative order rho which equals n. Okay? So that was the important thing. So in that sense, actually, yes, we introduced these new notations. And the Lie bracket. And we introduced actually in particular actually a Lie bracket here, where we said we want to analyze here pretty much actually this set actually of Lie brackets here. We take at first obviously adjoint f, obviously the 0th one in relation to g of x, and that is g of x. Then we take that g of x, we create the Lie bracket in relation to f, which f, I mean, just to remind you, f is the system drift, g actually is the input vector, and then we take that one, we plug it into the next actually Lie bracket in relation to f. And we are going through that step by step. And there was something interesting actually. I mean, well, in terms of linear systems, we saw actually something quite interesting. If we compute these Lie brackets for actually this particular linear system example, what did we get actually as a result? Sorry? Yes, yeah, thank you very much, yeah. So, I mean, in principle, actually, what we actually got out was actually, yes, I mean, with an alternating sign, we got the vectors actually of our controllability matrix. So, in principle, actually, what we are computing with this, these Lie brackets is some form of actually controllability test. Yeah? And, well, this is an analysis method which actually was developed by, or well, it's not the development, it's really very, very excellent research by a gentleman called Isidori. I think, well, it wasn't Isidori, then actually it must have been actually all his students and his co-workers. So, so Isidori, he wrote a book actually also on nonlinear systems. It's somewhere actually, I think it's called Nonlinear Systems, I'm slightly unsure. It's a Springer book. But to be very honest, I mean, yes, you can look into this book. But I think a good book, if you were curious actually to know a bit more personally, I think it's always also the book actually of Khalil. Yes, Khalil actually is written here, it's 2003, but there's so many new updates on actually Khalil's book. I mean, Khalil actually, his actually book actually has been quite actually generic and excellent actually, because it's rigorous, but even though it's rigorous, I think I still feel actually it's quite sensibly to read. Isidori's book actually, I think, came out about the same time, but I mean, I would say it's a bit harder to read. It's a harder read, it's not easy to read. Khalil, pretty much I read during my PhD, actually almost from front to the end, while Isidori's book actually I almost more use as a reference book, I would say. So, right, and this kind of analysis method actually pretty much obviously allows us actually to verify for nonlinear systems pretty much actually obviously two conditions. Two conditions which are allowing us then to say this system, the relevant system we are investigating here, has then an output. We can find an output so that actually the whole system is feedback linearizable with a relative degree actually of actually n, so actually the number of states in the system. So in that respect, actually, we were looking in particular actually then here at that matrix, and we said actually this matrix actually going up to from, I mean, having here n vectors, effectively needs to be full rank. And we saw actually that for particular examples, we need to test this matrix actually also in dependence actually on the state actually variables. So it's not coming up actually as a just constant actually the determinant actually of this matrix, but it's dependent on the state variables. So from that point of view, actually we have to make sure that actually this matrix is full rank within our full state space. Yeah? So it is actually, and that guarantees actually that kind actually of controllability at every single point actually within the state space. At the same time, actually, we needed actually, obviously, the extra condition that actually, if we take one of those vectors out, that the whole system is so-called involutive. Yeah, one of your colleagues actually yesterday actually asked some really good question. And that was a good question, actually. I mean, we looked at these vectors, and as I said, actually, I wasn't really keen, actually, this wasn't in relation to actually the analysis of actually a particular specific system, but here you have obviously two vectors dependent actually also an extra variable x2, and we computed here the Lie bracket from it. So we computed the Lie bracket, and then actually we said actually we wanted to test if actually the two vectors together actually with the Lie bracket result gives us actually obviously an overall rank actually of 3. So question actually is this vector space here, is this vector space involutive or not? Because that's I think that was the fair question to ask, because I mean we want to have in certain conditions obviously the involutive feature. So we are taking here actually, we're having actually a vector space which is defined by f1 and f2. We are taking the Lie bracket, and so if this vector space defined by f1 and f2 was involutive, what would we have to have actually as a result of that? Is it involutive actually, this vector space? Let's have a look. So we have a vector space which is called here delta. So we have f1 to fn. We're taking actually here two elements from actually that, I mean any arbitrary element from actually that vector space. Yeah? And create the Lie bracket. And the Lie bracket is obviously a vector again. And the Lie bracket obviously for the vector space to be involutive needs to be part of that vector space. Hence, actually, what does that mean to the Lie bracket? Is it actually sorry?
It will be also a function of the system.
It will be
A function.
a function. the Lie bracket has to be effectively linearly dependent on the original actually here, on the original actually vectors there. Yes? The Lie bracket has to be linearly dependent on f1 up to fn. So hence actually if the Lie bracket, hence if we look at here f1 and f2, we created the Lie bracket, then we looked actually at the three vectors resulting from that, and as a result of that the determinant was -1, isn't it? Okay, good. So does that mean actually the Lie bracket is linearly dependent on f1 and f2? Sorry? It's independent, yes, exactly. So effectively that means actually the Lie bracket is not depending actually linearly on f1 and f2. Hence actually this space is not involutive. Yeah? So hence the space here actually created by f1 and f2 is not involutive. Okay? So that's actually the result actually of that analysis. And your colleague asked me this, and yes, actually that's a very fair question to ask. Is this vector space actually involutive? No, it's not, because actually the Lie bracket which we created from that was actually linearly independent of f1 and f2. Yeah? That's what it is. So that's an important result, and effectively it gave us actually a good tool actually to do things. So so what we did was we actually were looking at f1, f2, we were looking at f1, f2, sorry, I probably leave it like this. And we noticed that obviously the determinant of this matrix was non-zero. Yeah? Hence, actually, delta is not involutive. As I said, I have typed up actually what I actually showed you yesterday. I will put this online towards the end of the week. Yeah? I will put it online at the end of the week. Actually, all these little hand calculations, I will put it online. But don't expect it today because I'm teaching tomorrow again. So actually, I put this on step by step. All right. So I think actually these were the tools, and we noticed obviously, in particular, actually, once we understand actually if a system actually is obviously state feedback linearizable, then we in principle need to find a H which satisfies actually these conditions here. That's what we essentially did. We used a small example, a second order example. We wanted to find actually obviously a H which guarantees us actually a relative degree of 2. Hence, actually, we had to satisfy this condition here that obviously this actually Lie derivative is 0. And in the next step, actually, we were lucky, obviously not lucky, that actually it was non-zero. Okay? So, in that sense, that was a quick summary. And I will go through actually this material here today, where I will talk about right, I will talk about actually feedback linearization for actually robotic systems. And robotic systems effectively, it works similar actually what we have done before, but I mean there's possibly some slightly different insight actually into the whole thing. And we possibly know that yeah, I mean robotic systems are actually modeled in a slightly different way actually, or better modeled in a different way than through an obviously differential equation. And we, well, obviously in the nonlinear affine sense actually, we slightly structure actually these slightly different. So actually the approach is very similar, but actually we'll go through that today. At the same time, we will start looking today also at adaptive control. So we will look at the first steps actually of adaptive control, model reference adaptive control, and we will have an example in particular of a first order actually system today. And we will try to understand why we want to have adaptive control. So why does that make actually sense? So from that point of view actually, we will then carry on actually to more generalized model reference adaptive controllers, but I don't think we can manage this today. So, right. Here, so-called rigid body systems, or actually in general, actually Newtonian systems, can be modeled actually in general actually pretty much as mass times acceleration equals obviously certain external forces. And in particular for rigid body dynamics, actually we can write this down in terms actually of a mass actually matrix times actually an acceleration vector plus actually so-called centrifugal forces, and where we have usually some form of Coriolis or centripetal matrix, which depends on actually either the position actually of a robotic system, a robotic arm system, or actually the velocity of it. Then actually we have usually a gravity vector, and in addition actually we end up actually with something like actually unknown actually kind of forces which are friction or yes, I mean extra disturbances. And we often have some form of actually externally applied kind actually of forces. So for instance actually we have in many ways actually, write this down. Wait a minute, I just want to write something down here. Later. I'll possibly show you at first here an example where we have here, there we have that kind actually of robotic arm. We will look at robotic arms of that kind actually of structure, and what we can see here. Can you see that? Does it work? That's a good question. If it doesn't work, then we're a bit, I have to resolve it actually in the break. All right. No, I think I have to resolve this in the break. Actually, It's working obviously on my computer, but it's a bit slow. I mean, the most simple kind actually of system in that sense, actually we could actually just simply write like this. Obviously we have mass times acceleration equals obviously some kind of external forces, and that actually would be pretty much obviously just a vehicle actually going on a path there. So and what we have often as well is some form of obviously damping forces which are actually unknown, and that might actually come in as well. So this is actually the most simple kind actually of system, and I will see that I get actually the simulation running then a bit later in addition to that. So the idea is pretty much obviously that that we need to understand actually now, because in general actually this mass matrix depends actually on, well, on the position vector actually of a robotic system, and also the Coriolis matrix depends actually on the actually position vector and the velocity vector of a robotic system, and the gravity actually also depends actually on the position. So for instance, if you have a pendulum, then the pendulum actually has actually the greatest gravity effect pretty much here when I have my arm obviously in the horizontal. Yeah? So from that point of view, we want to be able to compensate actually for these nonlinearities, while at the same time we want to introduce actually some form of linear actually closed loop behavior. So what we do in that sense we are reformulating pretty much the system to be able actually to have a similar kind of representation of what we had for the nonlinear affine system. In general, this mass matrix is here invertible. It's not always the case. And what happens then? If we can actually invert this mass matrix, then actually we're getting here actually, we can reformulate obviously our acceleration actually vector in relation actually towards here our input forces or torques, and we have here these added actually kind actually of nonlinearities. So from that point of view actually we have the system being actually a relative degree 2 system. So what we want to do is actually in principle actually cancelling actually these nonlinearities here. We want to cancel these nonlinearities, and we want to be able actually to introduce an extra actually linear kind of control scheme which effectively tries to actually introduce some kind of tracking controller. Yeah? So what we want to do is actually to introduce through that tau vector here, so as we can see actually tau is a vector in this case, q is a vector, and m is a matrix. M is a matrix which has the actually size of nq, where we have nq actually joint variables. So m is in that way actually an nq times nq actually matrix, and v actually is also a matrix which is an nq times nq matrix, and g is a vector, and f is a vector, and tau actually is a vector, which affects pretty much all our actually degrees of freedom. So what we want to do is, in this case, introducing actually a demand q d, where we want to see that our q follows actually our demand qd. what we want to achieve as well is essentially that QD dot is known and QD double dot. So we can plan for our demand. So we can plan for our demand QD, we can plan for our demand in terms actually of derivatives, first derivatives and second derivatives. Because actually tau affects all degrees of freedom here, tau goes effectively, we can in principle actually cancel quite easily actually Vm times Q dot, and we can cancel easily actually GQ. So in particular actually these two terms here, they're there actually to cancel these terms here. Well, in addition, if we actually have knowledge of our mass matrix, and if we have knowledge, obviously, of our demands, we can in principle actually multiply our mass matrix times actually the demanded actually acceleration. And we are introducing here actually extra terms. So KD here and KP are in principle then matrices which are some form of proportional and derivative actually kind of matrix. So we can easily actually cancel then here at first the nonlinearity and introduce here actually these extra terms. So as the next step, we're introducing then obviously these, we're having here KP and KD, and what we are getting is actually a linear closed loop behavior. This is in particular possible because M is invertible, and that's quite actually generic actually possibility if you have so-called rigid body actually robotic systems such as robotic arms. So KD and KP allow us actually in this case actually to create obviously a proportional derivative actually gain, and well in principle actually what we can do effectively here is we can also decouple actually pretty much all the degrees of freedom here. So how would we be able to decouple actually all the degrees of freedom, all the different actually, as we see here, M and V are not necessarily in this case matrices which are actually in principle diagonal. They are not, they're actually populated across the whole thing, and I will see actually that I can get actually my simulation running. So but we can actually decouple actually these dynamics by actually making KD and KP diagonal. Yeah? And we can choose actually each KD and KP specifically. Bless you. So what I wanted to do is actually, let's see that I can not, I will do it differently. Bit annoyed with that. Right. Ah, something is running. Okay, good. So it's running now. This is actually a robotic system which has 3 degrees of freedom. So it's a very simple actually robotic arm. Yeah? From that point of view, what we have here, let's have a look here again. It's so our mass matrix, possibly This here is our mass matrix. Our mass matrix is there in an inertia. Then we have there effectively a mass m2, which here is the end mass at that point. Yeah? So we have here a variable r. That variable r tells us actually what is the length actually of that robotic arm there. Okay? And then we have here a mass 2. So what happens is mass 1 and mass 2 is being lifted here through actually this degree of freedom. Yeah? So you have that. And what we get is then in addition a movement of actually obviously mass 2 actually in the horizontal direction. So we're moving actually this mass 2 in the horizontal direction, while actually we are rotating actually here pretty much also with our degree of freedom. So at the same time we have here pretty much written down the Vm times actually our q dot. So I write this down in a minute. So we can see here the Coriolis force of our rotational degree of freedom. And here that actually is an angle, and this is actually the length actually of r. And so that actually overall gives us here a centrifugal force. All right? Well, actually the gravity vector is pretty much that one there. So, as an example, we have then a Q, and I bring this up in a minute, which has a theta, which has a H, and which has a R. So, and I want you to actually look at these examples at home and try to understand this actually at home a bit yourself. I will upload this at some point, actually latest by the end of the week, actually in the next, possibly tomorrow. So effectively, what we have here is obviously an MQ double dot plus a VMQ dot. Oops, sorry, actually I have this actually, yeah, there's the 2m r dot, and then we have theta dot. Sorry for that. So GQ equals tau. Okay? So what we have here is at first obviously our m, we have our M, which is our mass matrix. There's that. I multiplied this here already out, our VMQ dot, which is that one there. And here's our GQ, which is that one. So here in this case, gravity actually pulls down. Yeah? And so we have a mass there, we have a mass there, we have a rotational degree of freedom, which is our theta, and we have a h which pulls us, brings us actually upwards. So these are actually here the three, actually, obviously this is the matrix, this is actually Vm times Q dot, and that is G. And this in particular here, if we look at this, creates pretty much here actually at first the robotic system. So we have here again replicated actually our M, our V, our G, and I have created here actually pretty much the nonlinear dynamics with actually an additional actually vector for the actuators. So what happens then actually, we have here the robotic system, and there actually we have a torque and two forces. I mean, forces leading us out and leading us up, and actually we can measure actually the rotational degrees of freedom. Here theta dot, we can measure actually h, which goes actually is the degree of freedom going up, and here's r and r dot, which is effectively the movement outwards. Yeah? So at the same time, we have here the controller, which is meant to implement actually the kind of cancellation. So this is the output vector, which has here V, G, M times actually the demanded acceleration minus actually pretty much obviously the difference of actually in terms actually of the measured actually values of theta, h, and r. So that's pretty much there in relation to actually the demanded values. There we have q d dot and so on. So we have there the measured actually velocities here, there, and we create this kind of nonlinear controller. It's a nonlinear controller because we have here actually v and g actually in there, and v in particular is a nonlinear actually kind of vector. So what we can do with this, we can create with this actually obviously a feedback linearized system. If we actually look at this here, we can see here we are measuring actually here theta, h, and r, and in principle actually right, we can see that actually that all the responses actually are essentially the same at the moment, because I have chosen actually kp and kd actually all the of similar value, and effectively we're just getting a linear response. So what we can do, for instance, I mean, at the moment the controller assumes that we have actually here a mass, the masses are matching. Yeah? At the moment actually the controller knows exact masses and exact actually also inertias. J here in this case is an inertia. So if I know actually the exact mass, well then things work out nicely. But if I actually just put in here actually a mass which in principle is actually lower, and the controller assumes now the mass actually is smaller than the true value, what do you think actually in particular for some of the dynamics will happen? it will not cancel out dynamics. We are lifting actually here, for instance, also masses upwards, isn't it? What will happen in this case, for instance? Just, yeah, no, you're right, actually. It will not cancel out all the dynamics correctly. Sorry? Overshooting is a possibility, yes, is a good idea. I just run it. Let's have a look actually what happens. So yes, I mean a bit of overshooting because actually yes, I mean but in particular actually also here this is the value for h, the degree of freedom, the translational degree upwards. We can see actually here there is actually also an offset error, isn't it? Because actually our masses are not cancelling anymore, or we're not cancelling anymore the masses correctly. Okay? So feedback linearization is a beautiful thing. Actually it works obviously still quite nicely. We are still quite robust in a sense, but in a way actually we possibly need to carry actually out maybe some extra kind actually of, or we need to add various other actually approaches in to make things actually more robust. And that's the obviously slight dilemma of a feedback linearization controller, that you actually don't know exactly actually what actually the parameters are. Let's have a quick break of about 10 minutes, and then I will come up with some movies, and then we go into adaptive control. And yes, I mean, I will put this simulation online, and I want you to investigate this simulation because I want you to understand it actually, and I want you to play with it yes, afterwards. Okay, good. Yeah.
Supervisor of the master's, right?
I will be, yeah.
Which ones related to?
I must admit, yes, I will, yes, yeah. The point is actually, I think I received emails where I must submit MSc projects, and I haven't done this yet because I've been quite busy actually preparing this, and I wanted to wait as well.
On June, July, the MSc project.
Yes.
Because really my interest is in robotics, my understudy is mechanics. So
okay.
I think for control more for the robotics part application of it.
Okay, yeah.
Haven't seen that much because
I mean, the control group, I mean, is very well known for its control actually expertise. But as you might have noticed, we are growing now at the moment quite a strong robotics initiative. That's also the reason why actually I was pretty much I joined here about half a year ago. So yes, I mean we do actually obviously projects, and I will do projects. I think actually 90% certainly actually in the area of robotics, or actually yeah, I mean it will be in the area of robotics, and there are other colleagues of mine, like Joaquin Carrasco, do that as well. And then actually there are, yes, I mean, who would be? I mean, actually Alexander Lanson does nowadays robotics projects because he actually looks into UAVs. So yeah, no, I will do a robotics project. I mean, I do actually mainly. I will do actually manipulate a kind of control problems in relation to human-robot interaction. I think Joaquin will possibly do similar things. That's my gut feeling. I have been interested also in the aspect of human-robot interaction, more actually of trying to understand what the human does. So actually, this will not be actually exactly the same actually things which I'm teaching here. This will be more actually of. Where are you from actually?
From South America.
Which?
Ecuador.
Ecuador. Okay, good. No, yeah, my postdoc is from Colombia. So that's
Oh, my girlfriend is from Colombia.
his wife is actually from Mexico. So actually, they're all. Yes. So I mean, yes. Anyway, so but so we have been interested actually in trying to understand what actually is the decision of the human in the next actually step. We are observing actually arm motion, and from that point of view, actually, we wanted to predict what is a human doing in relation to a robot. The robot in our case is actually then a car, and the driver actually is the human. Which makes things a bit easier because you're sitting actually in a car and you're completely actually actually encaged on it. Because I mean, if I was standing here, here's the robot, then I walk around. Actually, then actually it's getting a bit more difficult because my actions are a bit more versatile. Well, in the car, actually, the worst thing is that I actually turn back and look at my kids and look at my mobile phone.
And what about bike? You have more control over the movement of the bike.
Bikes, I've never done this really. I mean,
Yeah, because-
simply not because of. Yeah, I guess no, it's never been really of interest actually. Bikes. Yeah, I mean, because I've been doing so many things. I've been actually working in automotive. Bike actually more from an automotive kind actually of. I mean, cars can be actually modeled through a bicycle model. I don't know if you know that. So, from that point of view, actually, the bicycle model is actually quite good to understand the stability actually of the, the motion of the car. If you go actually along actually obviously roads with a certain camber and so on. So it's quite important in that respect. But problem is obviously that I haven't done bikes really actually, and certain things sometimes feel maybe I want to stay away from because other people have done it for much longer. But yeah, I mean at the moment I don't have really interest in bikes. But as I say, from a car point of view, I've dealt with cars, and then you're modeling actually pretty much just. In the most simple way, actually, I mean the stability of car motion through a bicycle model or bike model instead.
Yeah, because,
You're more interested in bikes.
No. It was just an idea that.
All right, okay.
Usually, I came back to the uni and never worked. So
I see.
ultimately, from all the lectures, I start thinking what I'm doing to control the bike.
Yes.
It's considered as some kind of control.
Yeah,
And I
it's
know that-
very tough. Actually, people have done this. Actually, there are very good actually control scientists who have worked on bikes. Grimble from London, Mike Grimble. It's very famous. It's not necessarily that I've done this.
Yeah, I'm more
It's
interested in something about robotics. Because my main idea is to have the control master's degree, because in Ecuador you just need masters to teach on the uni. I cannot stay for a PhD or anything like that. For my undergrad I was on a student scholarship, and the condition is that I go back. It's like a mistake.
I know this trick.
Escape
Actually, and
plan.
it's not a bad thing actually to do. I mean, I think actually it's a good scheme actually.
Yeah, the problem is they do not allow to stay for a third level of education. So it was the one that they pay and the one that I can choose by myself, and then I have to go back. So it's not like
No, I understand. Okay. So I mean, I will have some projects out more on the robotic arm and human-robot interaction kind of issues. I think that's maybe also, I mean, someone asked me about the robotic hand yesterday. Yeah. So And that might be actually also something that I might be doing. Yeah. So, yeah, catch up with the gentleman who was developing the all right, good.
Sorry, I still confused about this part.
Yes.
So it has to be ordered.
This has nothing to do actually with this one. It's more actually just an arbitrary analysis. We're looking just at F1 and F2 as arbitrary kind of vectors. And we ask ourselves, is actually this vector space created through F1 or F2 involutive? This is actually the test question. So it's not related to actually the theorem. This is more an analysis point. Yeah? So is this actually this vector space involutive? It's not involutive because actually F1, the Lie bracket of F1 and F2 pretty much creates a vector which is linearly independent of F1 and F2.
If it is involutive, the bracket of these two should
F1. Yes. That's the result of that.
this has a physical meaning.
This has no physical meaning at the moment. It's just an abstract. Yeah. In relation to this, actually only the example here at the back actually was sensible. Yeah. Here we try to look obviously at is the system at first obviously satisfying actually the conditions for state feedback and stability. So we actually looked at first at the rank condition, and actually we knew actually that the system, because here it's only G which makes up that kind actually of space there. Yeah, it's only G, so it's involutive. That was the good thing. A single vector is also involutive. Yeah? Okay, good. Okay. All right. Maybe is everyone in or? Okay. You want to tell the others or? I think, okay, goody. So, I mean, just also another actually quite simple example, which essentially it's a single degree of freedom example, is this one here. We have here an M. We have there we have there phi, and then we have here a tau. Yeah? And yes, and I think actually I got this here wrong because actually this has to be a plus. So this is a typical actually inverted pendulum example, and in that sense actually yes, I mean it's quite simple actually. It's also here actually it's nonlinear, and here we could just easily create ourselves obviously some form of, if we had here a phi d dot, a demanded, and phi d double dot. Yeah? And we could create ourselves obviously quite easily actually a controller which cancels actually here the nonlinearity, which is that one there, sine of phi, plus obviously now obviously ml squared times obviously phi d double dot plus ml squared times actually, then we have here kp, we have a negative feedback actually, so we have phi d minus phi plus ml squared plus kd, which is phi d dot minus phi dot. Yeah? So this is a typical actually just very single degree of freedom example which one can introduce obviously to look at this. And the nice thing actually here is, so our L, which is here the length actually of our pendulum, we are rotating obviously there around that, in this case is constant, so we are actually having here obviously our inertia ml squared, and we can easily actually invert actually our, if you wish so, our matrix actually, our inertia matrix, or inertia actually just value in that way. So what we get actually ultimately is obviously this kind actually of obviously closed loop behavior, which is a phi minus phi d double dot plus kd phi minus phi d dot plus kp phi minus phi d, and that equals 0, right? So, and we know that we can easily choose actually kd and kp to get some form of performance, and we're having now actually our closed loop system obviously in the dynamic variable of phi minus phi d, and obviously its derivatives. Okay. So we can design kd and kp appropriately. Choose actually some form of root for actually the characteristic equation. So what I want you to do actually, I want you to sit down actually and have a look at that simulation, because it will relate actually pretty much to your actually to your assignment then. Yeah. And want you to think actually how you, to understand actually this simulation. This would be quite nice if you could do this. I mean, it's quite hard to say actually I have used actually feedback linearization always actually per se, because as you can see actually if I change actually here some of the parameters, the performance changes quite a lot, isn't it? And in that sense actually there is actually quite a lot of extra actually kind of thinking and work actually necessary. And for instance we have used also adaptive control. Let me have a look. So this is a former PhD student of mine. He is now in Malaysia. He's an academic there, and he worked with me actually about 5-6 years ago actually on this kind of work, where we used actually a mix out of feedback linearization plus actually so-called agent-based control. I mean, there are colleagues of mine actually who also do agent-based control. And this is possibly a bit of an awkward kind actually of, no, we don't need this, sorry. This is a bit of a strange example in the first place. what happens actually, well, yes, we have used actually, for instance, also feedback linearization to be able to control these two arms. But what you can see is actually Nassir actually is moving actually one hand, and the other hand actually follows that. Can you see that? And so he uses actually, we use actually something else, which is some form of cooperative control. So there are elements of feedback linearization, there are elements actually of adaptive control, but in essence there is also cooperative control in here. What happens actually when you have flocks of birds, isn't it? They fly actually in a synchronized manner. You might have seen that. Yeah? And then you have one bird actually pretty much in front and the other birds are following. So they are synchronized actually in some sense with a certain distance to each other. So control scientists have been inspired by this kind of idea that actually, well, these birds are synchronizing just simply by actually information of the birds next to each other. Yeah? So they actually know effectively, there is one bird, okay, I need to follow that bird effectively at that kind of distance. There's another bird, I follow that bird actually at that distance. So effectively they try to keep actually this kind actually of flock by looking actually around, and then there is one leader. So we thought actually we can apply this kind of idea actually also to humanoid kind of robot torso. And this is work we did actually about 5-6 years ago. But what Nassir does actually, he pretty much has moved here that hand on one side while the other hand followed there. And in principle actually we have applied actually this idea actually of multi-agent control, where actually you have a cooperative control where one hand actually is being moved and the other one follows, and Nassir actually becomes the leader of this. And we didn't really understand in the beginning what are we going to do with this, but effectively what we thought, well, okay, if our hand actually is now synchronized more in a, not necessarily here actually in this kind of motion, but more actually it's synchronized towards some Cartesian space. So actually it's synchronized towards here actually there, and the two hands are actually at a certain distance from each other, and that actually in a Cartesian space rather than actually in a joint space, then in principle you can use this to effectively create some kind of human-robot interaction. The hand actually should be actually synchronized at the end actually, so he takes off actually his hand then actually there at the end. As you see there actually he has, so the two, yeah, as you see actually the two arms are synchronized actually. The only thing that he actually keeps obviously there pretty much a guidance towards that arm. So it's that kind of leader actually follower kind of relationship. And if a robot actually is clearly actually stronger than actually the human, actually that actually kind of relationship is quite important nowadays also in production actually environments. So the other thing actually which we got this one here. Let's see actually which one is that here.
I have made contact.
Yeah, I'll possibly show you that. There's another one actually. I possibly wanted to show you this one here, but I didn't actually bring that. But what I wanted to show you with this one here is no, I didn't bring this one actually, that movie. I'll possibly show you this one here. So this is the kind of compliant controller.
I have made contact. I am listening. I am going to be missing.
Yeah. So you have seen this compliant controller in action before, but so what we did here actually, we used that compliant controller, which obviously was not capable of going through that little actually cushion because it was actively compliant actually in a human-robot kind of interaction task. And as you can see, Said actually, well, is in physical interaction with the robot. Yeah? And you can do that only because we have that kind of model reference behavior of a mass spring damper system. Yeah? You have that kind of model reference behavior of a mass spring damper system where we actually are sensing actually the torques and forces exerted actually onto that robot arm, and that actually is given to the virtual mass spring damper system and changes pretty much actually the tracking behavior of the robot arm. And that makes the robot arm safer. If we did this obviously with an industrial arm, which is not capable of actually sensing torque and was not capable of having actually these active control schemes, you would effectively get actually injured. So if you go to industry, actually look at some of these actually industrial robots, they're usually all encaged in safety cages. Yeah? Because actually, I mean, they're not actually able to sense any kind of person opposite. But nowadays, actually, there are also these KUKA LBR arms, which are used actually in production with the human very close. So actually, I mean, the idea is pretty much actually of having actually a robotic actually system which helps you actually to do the strenuous tasks, while the human obviously is capable of doing actually more kind of intelligent steps. And here is the idea actually here, this was a simulation of some form of, yeah, there's a cup. The cup is actually being put into a bin. Maybe it's in a hospital where actually then as someone actually interferes with the robotic arm, and obviously the robot actually needs to actually pretty much obviously safely actually stop the action. Yeah? That was the kind actually of idea we had at that point. And that actually is enabled through actually a model reference adaptive controller with us here. And that's the important thing here. Oops, now we want to. So you hear there is also a higher level kind of action on top, actually, where the robot obviously then actually senses obviously that kind of interaction and wants to actually introduce obviously more of a new actually form of action in terms actually, shall I continue obviously with throwing actually the cup away. But the low level actually controller is the compliant controller. Okay, good. So that is an example. And but as we see actually, I mean this, if we had to identify here all the masses and inertias, we would have a bit of a problem. Yeah? We would have to actually sit down and have to actually identify very well actually what are the parameters of this robot. And so what we decided then actually, okay, good, in our research we go adaptive. While other people actually have done actually other things. So they actually have tried to identify actually the systems very well, and they have actually also, I mean, we have used also methods called sliding mode control, for instance, which we are not teaching here right now. So this is possibly this motivation why actually it is sensible actually to do adaptive control. Yeah. So here in the first place we will look mainly at first actually at linear adaptive control, and from that point of view actually we will look in particular at model reference adaptive control. Model reference adaptive control actually, I possibly try to draw it out a bit. There is no, I will again put some of this actually again onto. So usually we have a control loop. Yeah? Our usual control loop actually looks like this. We have this kind actually of behavior. We have a plant. We have an output Y. And we have a control signal U. And then we have here actually a controller. And And that controller is effectively affected by obviously some form of actually demand R. Yeah? I'm not putting actually here in the negative feedback loop in there. I'm just simply saying actually right now this is just going in here actually through actually obviously some feedback action, and there's some computation happening in here. Yeah, that's the usual kind of control loop. And yes, we usually have here negative feedback, so actually we're creating here actually this kind of behavior. But this is possibly a fairly generic kind actually of control loop. However, actually now we actually say, okay, good, there is possibly a demand R, and we want actually our output to follow actually some very special kind of reference model. Okay. And there is then actually also, the reference model has an output ym. So, in principle, actually, we want that y and ym actually are obviously matching each other. So, we want this error here actually as a result of that to become 0. Right? And well, one can actually design actually a controller so that actually we follow actually the reference model. And if we actually have, in principle, actually a clear understanding actually what the plant model is, then we can create this controller quite easily. And I will show you actually this as an example actually today for a first order plant. But if we don't know actually the plant parameters very well, then we have no other choice but actually to introduce some form of adjustment mechanism. So there is actually some form of adjustment mechanism, so an adaptive or adjustment mechanism, which effectively is our adaptive law. And we have some parameters which we need to adjust. So there is actually some parameters which we usually call theta hat. And the adjustment mechanism is usually the derivative of theta hat with respect to time. And this is something we need to derive. So, so that's the question actually. What is our theta hat dot? Theta are parameters we don't know, and we will see actually where these parameters come from. And theta hat are the estimates. So actually everything with hat is usually an estimate of some parameter we don't know. So we are getting actually then out here actually our theta hats, and they are actually affecting actually then our controller. So what is interesting actually, this adjustment mechanism is usually not only driven actually through actually E, but it's also driven actually through actually, in our case, through actually Y. And also through R. So that's a bit hard now, because I notice that's a bit difficult to put in here. But yes, so I just put this in here. And effectively, in our specific case, which we will look today, R and Y will affect actually this adjustment mechanism. But what we want to do is effectively that we are actually following here our reference model. We are having here a demand R. That demand R affects the reference model, and we have a so-called output Ym. That output Ym in principle actually has to be compared with our plant output Y. So we want that actually this kind actually of reference model is pretty much the dynamics for our closed loop controller. So this is actually in contrast actually to actually the kind of controllers which often exist as well. Right? Because we still don't have that. But again, obviously, I will put this one again also online. This is very much in contrast to some of the controllers actually, which are often used actually as well, self-tuning controllers. In principle, actually, the kind of these self-tuning controllers, I will have one self-tuning controller actually example later actually after actually we have discussed actually model reference adaptive controllers. I will have that actually as an example for the robotic system. Well, in the first place we will focus really on model reference adaptive control, and we will see actually that we create controllers which follow this kind actually of dynamic behavior. Let me see if I manage to bring up possibly an example here from my simulations here. Yes, and you will understand this later then. You will understand actually this kind actually of simulation later when we have gone through this. But if you can have a look here, there is actually here our plant, which has an input U, which has an output Y. And here I have created actually some form of reference model, and that is a demand R. So effectively what I want to achieve is that actually Ym is the demand for our output Y. Sometimes that's quite useful because actually the reference model creates possibly some smoother form actually of trajectory. So we will revisit this actually a bit later then. It's just simply that I want to show you effectively what can happen obviously if we actually simulate this. So here we can see actually Y as an output, and there's Ym. So Ym actually is a first order behavior, and as we see actually Ym is the result of a first order behavior. So we have a quite nice smooth kind of trajectory. And as you see actually also, I mean, our output Y is not always following extremely well the demand obviously Ym. I will explain to you actually why is that the case. Actually at first, obviously, because we are changing here parameters quite strongly. So we have here in this case, the yellow is our output Y, and our Ym is the demand. So actually it's nice and smooth. The our blue signal is the demand. It's nice and smooth. And that's actually possibly the advantage if you create here, for instance, actually in MATLAB, some kind of more random kind of demand sequence. It's quite actually, well, it's essentially a step kind of demand. It's discontinuous to some extent. And it's getting filtered actually through the reference model. So actually it creates possibly dynamics which are actually a bit slower than actually the kind of dynamics you have created through R itself. So we want to follow that Ym here. And we're comparing actually here, obviously ym with y, and I will explain to you that later how it works, because actually you will understand actually here is the so-called adaptive actually mechanism. So this kind of reference model is helpful actually to create obviously some form of dynamics which are a bit smoother and possibly a bit slower, or actually more suited actually to the kind actually of environment you want. So well, the steps actually of designing an adaptive controller. The steps of designing an adaptive controller is pretty much at first, obviously, in our case, in the first case, to actually design a model reference controller. So the controller which actually allows us actually to follow actually our nominal model. And then actually we need to choose pretty much an adaptation law, and we will see that we can do this through actually Lyapunov analysis. So, and then actually we have to analyze actually pretty much for stability. And I would almost actually say that actually these two steps, you often combine them. Yeah, you actually combine the analysis and the finding actually of the adaptation law. So what happens is that we look at first actually at a very, at a first order example where we want to understand actually how we can actually create obviously some form actually of model reference controller. The plant is a first order system. Our reference model is also a first order system. So if we write this down, we'll see actually, so our reference model in this case actually is pretty much something like this. So we have here YMS over RS equals obviously BM over S plus AM. Yeah? And then we have, in addition here, our plant, which is pretty much obviously then Y of S over U of S equals BP over S plus AP. Okay. So, and we want that, this is the reference model, we want obviously that our controller here, the controller there makes actually that error actually is obviously to 0. And that's the kind actually of target we want to achieve at first, before we understand actually how to actually create an adaptive kind of behavior. And then in the next step, we actually create that adaptive actually control behavior. So if you look at the next step here, there we have actually this kind actually of equation written down, which is effectively, well, yeah, a bit unpleasant, but not that unpleasant, because what happens is that we're simply taking our original equation y dot equals obviously minus AP times y plus BP times u, and all what we're doing here in this case, we're just adding here actually at first AM y, and we're also adding here y times AM. Okay? And now we are just reformulating this here by pulling out actually here the BP. So BP, sorry, is minus AP over BP times Y plus U plus AM over BP times Y. And that can be just rationalized then obviously to this kind actually of behavior there. Good. U minus AP minus AM over BP times Y. Okay. So what we also have is pretty much our model reference behavior, and we say actually we want to drive actually Y minus Ym to be 0. Yeah? So we know that actually we have Ym dot plus AM Y M equals Bm times R. That's our model reference behavior. All what we're doing now is just simply taking the difference actually of the two and taking care actually that actually the R actually appears within this bracket there. So by saying actually that we have here E equals Y minus Ym, we can just write now pretty much obviously at first there obviously E dot plus AM times E equals obviously, there we have then BP Y U minus AP minus AM BP times Y. I just leave actually this one still outside because there's Bm minus R in there. And in the next step we pull this inside the bracket, and then we have essentially exactly what is actually written there. So in the next step we pull this inside. U minus AP minus AM over BP minus Bm over BP times R. Right. So the interesting thing is obviously that we have here E dot plus AM equals E. And this creates actually, well, a first actually kind of idea how we can achieve that actually Y and Ym converge to each other.
There should be a Y.
Sorry, yes, yeah. Good, thank you. So this creates actually a first idea how we can get actually an idea of what we can do with this here. So first of all, we have here created actually an extra variable which is AY, and there is actually AR. Okay. And if we know these variables, then everything is fine. It's not really complicated because all what we do is essentially we're creating ourselves, obviously here, a new variable which we know. If we know all our plant variables, we certainly know always our model reference behavior variables, then we can just create this. So it's that kind actually of thing here. AM times E equals BP. U minus actually AY times Y minus actually AR times R. And the trick is now just simply to say, okay, good, let's actually reformulate this and say actually u equals, in this case, ay times y plus ar times r. What happens is that we have here E dot plus AM times E equals 0. So we have chosen our control signal pretty much the combination actually of a set of actually known parameters and actually in relation to y and r. Well, having this kind of behavior here actually is this, I mean, E is obviously, as we know, is y minus ym. These dynamics are they stable? Yes, they are, isn't it? That's cool. So these are stable dynamics as a first order system. Hence, actually, if we just choose our actually controller like this, then we have stable dynamics which drive actually our actually output y towards actually our demanded output ym. So that's a so-called model reference kind of behavior, and that now fits into this kind actually of behavior here, where we have actually not yet an adjustment mechanism. This is just that, and we have designed this kind of controller given actually a plant there. All right? But now the question is actually, what actually happens if we don't know this? So what if we don't know actually our plant parameters very well, BP and AP? And that actually is the kind actually of question we need to ask ourselves. What if we don't know actually AY and AR very well? Then we have to use some form of, estimate for it. Yeah? I mean, we do not know, obviously, AY, AR, so we have to use an estimate. The use of an estimate, and the estimate effectively we call this usually AY hat and AR hat, right? But that actually means we have actually suddenly actually the dynamics are not anymore obviously as beautiful actually as we have there. Okay. So, U is changing now, which is now AY hat plus times Y plus AR hat times R. But that means actually our closed loop behavior based actually on this one here changes. And we need to understand how we actually create actually the so-called adjustment mechanism which guarantees us actually closed loop stability. So first of all, we need to introduce actually some form of error. Another error. We have already a control error, if you wish, so which is pretty much this one here. But now we need another error, which is called AY tilde, for instance. So we have AY minus AY hat. Okay? And we need to understand how we can deal with actually, and obviously making that error obviously small, or not even small. Actually, our major actually objective is actually to keep E small, isn't it? That's what we want to do. But we don't necessarily need to have actually this error small. That's the interesting thing. So now actually we have there also AR tilde, AR minus AR hat. Okay? And what is also quite important is that we always assume that actually our parameters here in this case, AY is a constant as well, and AR is a constant, right? So we are not changing parameters here really. It's just that we don't know them. In my simulation you will see I'm a bit naughty actually, I'm pretty aggressive actually. But we are assuming pretty much also AY and AR actually constant. And that makes our life a bit easier actually also in terms actually of that analysis right now. So, well, we can see actually, well, we have this one there. We have obviously this new controller there, and we have now these errors. Hence, actually, we can substitute actually our controller, which is here E dot plus AM, E equals BP minus AY tilde times Y minus AR tilde times R. Okay. And that's because actually I pretty much just used my definition here and I get this kind of behavior. However, I mean, now I have the dilemma actually, we have that extra term at the end. And we need to understand actually how actually can we design obviously an algorithm which pretty much adjusts these estimates. That's the big question mark. The interesting thing actually, Lyapunov theory helps us with that. Analysis. Right. I mean, one thing actually is to create actually a Lyapunov function, and it's written in there. Well, evidently, you want the error, the control error in there. Yeah? You want the control error in there. But what you want in there as well are actually these parameter errors as well. So what we do actually is we add, well, pretty much actually something which actually contains the parameter errors. Yeah? So we have to have this, and now we have extra multipliers there. One is we will see actually is, well, the 2, we know that this is always coming out from the Lyapunov analysis because actually we have quadratic kind of Lyapunov functions. So that's there. We introduce extra tuning gains. We will see gamma R and gamma Y is an extra tuning gain. Yeah? So gamma R and gamma Y actually have to be positive. Yes, I mean, then we introduce in addition actually a plant parameter which we know is constant in principle, so in that sense actually, and to some extent one can say actually that's a bit of a, yeah, just for scaling actually the whole thing. So, I mean, some people may not even put in the BP, but I think here it just simply fits nicely. So from that point of view, we have here a Lyapunov function. And we can use that Lyapunov function now to analyze actually the system. And some nice thing actually is already here. We know effectively that actually if we set this one here to 0, then this one in principle actually obviously is the E would guarantee actually, or would be actually a nice Lyapunov function to prove actually stability actually of the system here without actually that term there. So the E in that respect actually is well chosen. Well, this will be here pretty much the big question mark. So we have to have here E times E dot plus BP gamma R. And here we need to be a bit careful now. So we have there, sorry, the 2 is gone. We have a tilde R there. And, right, too many brackets now, sorry for this. So, minus, yes, exactly, minus AR hat dot, isn't it? That's what it is. So that's why I put all these fancy brackets there, and some actually were not really necessary. Simply because actually AR is constant and AY is constant. We just don't know them. And once they actually change, actually that becomes obviously a bit more interesting. So now we have here the same gamma y, and there we have AY tilde minus AY hat dot. Sorry, too many brackets. But you can just eradicate those brackets. Actually, it's just, and I could have just simply put the minus there, but it's just simply trying to show you. Obviously, we have that. I mean, extra actually kind of fact that AR and AY are constant. But that actually, I mean, becomes then interesting. Actually, here, well, we said actually our adjustment actually law depends actually on A hat, or is actually a law expressed actually in terms of the derivative of our actually estimate, of our estimates there. So actually we may want to use this here in the next step. So what happens now, we have here this one there, and we can in principle obviously add all this there in. So we have here minus AM times E plus BP minus AY tilde Y minus AR tilde times R, and then we can just close this up. And there we have this minus BP gamma R, and there we have AR. All right, sorry. So there is AR hat dot plus obviously a minus BP over gamma Y AY tilde times AY hat dot. And that becomes quite interesting because I mean, sorry for this. I mean, here this one actually is quite comfortable because you guys have seen this before. Actually, here we will have minus AME to the square. Yeah? But here we have AY and AR tilde. So actually these are AY and AR tildes. There we have that one as well. So we may want to factor things actually according to that. Right? So we may want to factor out actually this, and just bring those together and see actually what happens. I'm sure your handwriting is so much better than mine. Right. Let's have a break again. 10 minutes, and then we continue. Okay? And okay.
I want to ask in this case, no. In this case, we have tested this guy.
Yes.
And I want to ask, in this case, why we test this guy instead of G, F1, F2, and F1, F2?
Sorry, why we do this? We essentially, I mean, in all honesty, I mean, it's an example. It's not related to Theorem 7.1. It's more related to the fact that actually spaces can be involutive. So we look actually at F1 and F2,
Yeah.
at that space created through F1 and F2, and see actually if this space is involutive. Yeah?
So this guy only indicates F1 and F2 is even.
The space actually created through F1 and F2 is not involutive because actually the Lie bracket of F1 and F2 is a vector which is linearly independent of F1 and F2.
Yeah.
Okay? Is this actually... This was pretty much the result of that, and at the same time we actually also understood actually what is the rank actually of the space created through F1, F2, and the actually bracket of F1 and F2. So we're trying to understand actually various concepts here. Is effectively the space created through F1 and F2 actually involutive? And actually is actually what is the rank actually created of the space of F1, F2, and actually the Lie bracket of F1 and F2? No?
No.
Confused. So I mean, if I say F1 and F2 are actually two vectors,
Yeah.
and they're well, obviously vectors dependent also actually on variables such as x2 and x. So think of two vectors.
Yeah.
So, and you want to understand, is actually a third vector
Yeah.
linearly independent or dependent on them?
Yeah.
Okay, good. And that third vector is the result actually of our Lie bracket.
Yeah.
Yeah?
Yeah.
And as we figured out, it's linearly independent from actually F1 and F2. Yeah?
Yeah.
Hence, actually, well, the space created through F1 and F2 is not involutive, because actually what it means actually when a space is involutive, you can take actually any kind actually of element of that space, and the Lie bracket of that has to be inside that space. Hence actually the Lie bracket has to be linearly dependent on actually any vectors inside that space.
Yeah.
Right?
Yeah.
Okay, good.
Yeah.
So here actually the distribution is involutive if actually any element from that space
Yeah.
is actually, the Lie bracket of it is actually inside the space. Which is for this example not the case.
Yeah.
Yeah? So we've just obviously learned in that sense at first obviously how to compute actually a Lie bracket, to test actually if the space is involutive, and to test actually what is the rank actually of the space created actually, or the dimension of the space created through F1, F2, and the Lie bracket.
Yeah.
So pretty much three different results in a wider sense.
Yeah.
Yeah?
So there are different examples.
This is not related to Theorem 7.1. This is just simply related to actually the fact that we want to test actually if a distribution is involutive and what actually is the dimension of a space. Yeah?
Yeah.
Okay. This one here is pretty much actually, this example relates to this one here. Yeah?
Yeah.
There we actually looked at the nonlinear sum example and we said, okay, good. This one here, we know actually that actually this space was made up only of G.
Yeah.
Hence actually G, the Lie bracket of G to itself is 0.
Yeah.
That was cool. Good. So the space created of G actually is pretty much, that means actually the Lie bracket is 0, hence actually the space created by G is involutive. Right?
But what about
Here, that one. We don't have F here in here because we're having only a second order system.
Yeah.
Hence we actually don't need to compute actually more than one element actually in our space here for that second test. Yeah? Because we're going from Gx up to actually the adjoint actually of order n minus 2, which is actually 2, n equals 2, 2 minus 2 is 0. But actually the adjoint, the zeroth adjoint is pretty much G. Yeah, so it's only one element in that vector space. But actually here, because we are of second order, actually the matrix we need to test actually for controllability, there we have 2 elements. And that we did test, and we know effectively that as a result of that, here that matrix has obviously a rank of 2 because the determinant is always non-zero. Yeah?
I see.
So we have 2 tests. One test was pretty much testing actually for, is the space of G actually only by G created through actually, is it involutive? Second test is effectively our controllability matrix, effectively obviously full rank. Yeah? And both tests passed. Hence we could actually compute as a result of that a H which satisfies actually that we get actually a relative degree of 2.
Yeah.
Right?
Yeah.
Good.
Yeah.
Okay.
But I want to ask, in this case, F1, F2.
It's not related to any dynamic system. It's just 2 vectors.
Yeah.
Take 2 vectors, take them out of actually anything, and see if they're involutive.
Yeah.
Yeah? It's not related to a dynamic system. It's just actually 2 vectors and understanding if these 2 vectors create an involutive space. Yeah? Has nothing to do with any dynamic system at that point. It's just saying, is this vector space created by F1 and F2 involutive?
So in this case,
In this case, we have a dynamic system. We have actually a nonlinear affine system with actually an F and a G, and we obviously have here a differential equation.
So if we want to prove this system is
Feedback linearizable.
is even so we see Gx itself.
Well, in this case, we are looking just simply, obviously, at that theorem here, and we want to understand, is that system state feedback linearizable? Yeah?
Yeah.
This here was just simply, is actually the space here, is it involutive?
Yeah.
Here actually we have then actually obviously various questions to answer. There we have to answer actually, are these various Lie brackets here, obviously in this case only G of x, is it involutive? Yes it is. Is our controllability matrix full rank? Yes it is. Hence we can design a H so that the system obviously is fully feedback linearizable up to a relative degree of 2.
Yes.
Okay, cool.
Okay, thank you.
Brilliant.
One question without but we have
Yes.
the Lie bracket will be.
Well, you have to choose then actually pretty much any 2. You
I can have just 2.
I mean, if you wanted to actually now test if this one was involutive, you would have to pick always pairs of 2.
Okay.
You have to actually, I think you have to actually have them 1, 2, 3. So you would have to test 3 actually Lie brackets.
So
That's quite a nightmare, yes.
F1, F2.
But yes.
F1, F3, F2, F3, to do like this. But in our case yesterday, we just have this one. So we are just with this one.
That was cool, isn't it? Can we just continue now then? Because I need to go through my. You ask me later, yeah? Hopefully but let's continue now. We will have more time to do this. Yeah, I need to continue. Yes. Okay, guys. Thank you very much. First people are falling asleep. Right. No, thank you for sticking around. it's obviously a long day, and I do appreciate actually it's also quite a bit to take in, especially actually yesterday's lecture, and we will always have the chance actually to discuss this again. It's definitely possible. I mean, not infinitely, certainly, not infinitely. So, good. So effectively we have here v dot, and well, one thing actually is nice, we have am e squared. We are happy about this. Why are we happy about this term? Sorry? Because it's a squared term, it's negative essentially if e is non-zero. Good. Problem solved. So now actually we have more terms, and those terms are actually possibly a bit more troublesome in a sense. Yes, so I think I made a mistake here, but on my other thing here. So, well, one of the things is actually, okay, good. So we possibly want to see that we actually bracket out here actually, let's say, plus some form of ay there. Sorry, ay tilde. That's the first thing. And as we see there, we go there very, very slow now. Let's have here ay tilde. So we have here e, bp, and y actually. But then actually we still have a minus there. So we have to be a bit careful actually, not that we're messing things up here. Good, brilliant. Then actually we have here another ay, which is minus there we have a bp over gamma y, and there we have obviously ay hat. It's not going too badly. And again,
It's a dot.
yes, the dot. And I just wanted to say, if you spot a mistake, just tell me, because I'm known to make mistakes in these situations, so don't worry about it. So mine is E, and BP, and then we have an R there. And now we have here minus BP, there we have a gamma R, and then actually we have the AR, the dot. Okay. So that's the interesting thing. Actually, now we have here, obviously, these two extra terms, which in principle allow us actually to define actually an adaptive law. Let's go possibly one little step further, which effectively actually is, well, I mean, in a way important. I mean, we are happy actually about this term. This term actually is cool because actually we can just simply, well, ignore it to some extent. Let's pull out BP, because it gives us actually an important fact actually. Minus E y, but what happens actually here? I put here a signum BP. Yeah? And now 1 over gamma y. Have you found another mistake, or So plus, then we have AR tilde BP. So the BP has actually a quite important kind of meaning actually here, because we have minus E times R times actually signom of BP minus 1 over gamma R. This is the gamma, whatever you think. Sorry, and this is a hat, and there we have that.
Why did we get a signal?
Yes, so I mean this was pretty much actually this is the trick actually now, because we can in principle now design actually our adaptive law. Our adaptive law actually says, because we don't know any better for the moment, we just simply say actually, hey, I mean we are happy about this, yeah? We are possibly a bit confused about all this. We are confused about this. So why not just simply saying, let's get rid of it. Let's get rid of it by actually designing an adaptive actually kind of law, which effectively says, hey, AY hat equals obviously gamma Y minus EY signom BP. Next one is AR hat dot minus gamma R ER signom BP. Well, what is quite interesting here? This law is driven. I mean, let's just rethink actually what actually is our control law. It pretty much was obviously. Where is it again? Yes, there it is. So it's AY hat Y plus AR hat R, and then we have well, we know that we have to have E equals Y minus YM, and we need to create our YM, which is pretty much obviously a result actually of YM over R equals obviously well, yes, BM over S plus AM. Okay, so this is our adaptive law here. Actually, if you just cover this all up, I mean, in principle, yes, we have a first order system. We have a first order actually kind actually of so we know that we have a first order system. Actually, our plant is a first order system of a very specific structure. But actually our reference model, we know this because we want to actually have a certain desired reference model. And certainly as a result actually of our reference model, we get a certain output Ym. And we can always actually create a difference here. Here we suddenly have an estimate of a Y and AR. The estimate actually of a Y and AR is driven actually through the error, is driven by actually our plant output, is driven actually by the demand, and we have here a gamma Y and gamma R. These are just positive constants, yeah. And the only thing we need to know about the plant actually is the sign actually of obviously of our input gain, yeah. So effectively, I mean, the sign of our input gain is pretty much telling us, are we having actually, how are we pushing forward in a negative or positive sense? Yeah? That's the only thing actually we need actually about this adaptive controller and to know about actually the model. In a way, actually, we still need to know that it's a first order system actually of relative degree 1. But
It's not the signal function, it's just sign. It's not the signal function, it's just the sign.
Signum actually, or signum is the sign actually of BP. Yes, signum, yes, sign. I mean, yes, is the sign actually, but signum, okay, is the sign, yes, if actually to be here clear. So, yes, it's just obviously positive or negative. So that's the only thing we need to know. But we don't know much else about the plant. That's what I'm saying. Yeah? Okay. So that's why actually this adaptive law is quite flexible. In a way, actually, it's quite actually nicely to use. The only thing is actually we end up now with v dot equals minus am e squared. Yeah? So this means actually that in principle v actually remains bounded to some extent, isn't it? But it doesn't mean actually that actually we don't know much about actually at the moment what's happening here. Yeah, we don't know actually what happens to the error actually of the system. But well, I mean, if you look at it, obviously you can in principle now integrate the whole thing. And we know that obviously we're integrating actually both sides actually now from 0 towards infinity or so, or 0 to t. V dot equals obviously minus am. There's an integral from 0 to t. There's a d tau t. You can also integrate towards infinity. It doesn't matter actually in this case so much actually, but of course actually you have an integrand which is tau then. And ultimately actually you come up actually with the fact that cool, good, we are ending up actually with this kind actually of integral here. Actually we have 0 to t e squared. Yeah, I mean I use an integral tau now here, and then actually we have v0 minus actually vt over am. And certainly actually we know that in principle actually that is obviously always smaller than actually some constant. So smaller than infinity. Actually there will be always some constant which depends actually on the initial state. Because we know that actually the initial state actually, well, defines pretty much, obviously there is some k. And usually we want to have t going towards infinity. So everything what we know right now is actually only about, well, we know that actually our v is bounded. We know that this integral is bounded, but we don't know much else. So we know essentially that this one is bounded. Can we actually say that anything about actually the convergence of this? Yeah? That's the question. Can we say actually anything about the convergence? What happens to, I mean, we know this is bounded, but what happens to et over time? Does it converge actually to 0? And that's the question actually. Does it converge? Does actually et converge to 0? Right? So, and there actually we have something called Barbalat's lemma. And Barbalat's lemma is it's quite a technical lemma, but the point is actually I was thinking actually to some extent I would want to see actually if I can prove that lemma actually in a more simplified form. Depends if you want to, I don't know. So Barbala's lemma actually says, and I thought, well, let's have a look actually what actually we are getting here. Barbala's lemma says actually a function which is f, which is integrated from 0 towards infinity, and where we actually see that actually this integral actually has a finite value, and f is then so-called uniformly continuous, actually is a stronger form of continuity, then f actually converges to 0. So this is a bit of a question mark. Actually, what is uniform continuity? I mean, in particular, actually, in general, actually, it's, for instance, it is sufficient I mean, f is uniformly, and I want to actually use a slightly different formulation of this to be able to prove this to you. Now we have about continuous if it's not if and only if f of t is actually bounded, so it's some smaller than k, and f dot of t is also bounded. And if this is the case, oh, sorry, actually I forgot to switch. Very, very sorry. F of t is uniformly continuous if, not if and only if f of t is bounded and f dot of t is bounded actually as well. My mistake. And in this case, actually, I mean, we definitely can actually also say, actually, okay, good, actually, the integral from 0 to infinity of f of t, if that actually is also bounded, dt, and the k can be just large enough, hence, actually, the limit of f of t towards infinity goes to 0. If you want, I can provide you actually with a proof of this, because when I read actually a slight variant of this before, I thought actually that's quite interesting how actually one can prove it. I could possibly try to actually see that we can actually prove this. Let me show you at first the simulation, and then I can see actually if I have some time, maybe I can. Who wants to see a proof of this Barbala's lemma? Any chance? Any excitement? You want? We will try, but I will not prove exactly Barbala's lemma. I will try to prove something slightly different, which will be sufficient actually for you to use. Okay, cool. But let's have a look actually at the simulation again. The point is actually, before we look at the simulation, well, let's have a look actually correctly here what we are doing. Right. We possibly should verify actually that actually this is indeed holding true. That's the first thing. I mean, in terms actually of our equation there. So, well, we know in principle that So the first thing is, we know in principle that our Lyapunov function is either decreasing or constant, isn't it? Yes? So that means actually E is bounded at all times. I mean, our Lyapunov function is either decreasing or constant. That means actually E is bounded, our errors are here bounded. Okay, good. That's quite important. So E is bounded and our errors are bounded. Let's have a look back actually at the dynamic equation here. We know that actually if E is bounded, so meaning actually our error in ym in relation to y, then also y must be bounded, isn't it? Okay. Let's write this down. Actually, I just want to go through the logic actually of being able to use this actually theory, and then actually we will okay. So we have certain relationships which are important here, so that we can verify actually that our theorem holds. So E dot equals actually minus AM times E plus BP AY tilde times Y minus AR tilde R. So 1. So V is bounded. So this follows from 1. But that means actually also E is bounded. That means actually that, I mean, E is actually here Y minus Yn. And that is bounded. So, but Ym is bounded at all times because actually our reference model is bounded. So Ym is bounded because reference model is stable. This model is stable. Right? And we have certainly, we should always choose a bounded R actually ourselves. Why would we choose actually anything else than an unbounded R, isn't it? It's our choice. Yeah? So R is bounded. Okay. So that means actually Y is bounded. Okay, but if V is bounded, then also AY tilde is bounded. And AR tilde is bounded. Good. Okay. Sorry. Right. So now all this stuff is here bounded. So effectively on the right hand side there's only bounded stuff. Yeah? It's all bounded. Cool. So hence E dot is bounded. Right? If lots of variables are bounded in relation to each other, we only do multiplications and additions here, so we stay bounded overall. Okay, good. So E dot is bounded. Hence actually E dot is bounded. So E and E dot are bounded, so effectively we can apply, in principle, Barbalas lemma. Yeah? We know now, if we apply Barbalas lemma, then actually our f of t is essentially e t to the squared. Right? And so yes, so I mean our f of t is e t to the square, and we can apply actually Barbara's lemma. Hence e of t, right, the limit of e of t goes towards infinity, is 0. Hey. So this is Barbara's lemma, and we can apply this actually when we see actually let's go back here. We can apply this when we have actually these when we have these Lyapunov matrices, the analysis here, and on the left-hand side, actually, well, if we wanted to have actually some form of, I mean, here in this case, actually, we are not getting the result we would like to have. What do we want to have usually actually on the right-hand side actually of our actually Lyapunov derivative? What do we want the function to be? Yeah, negative definite, isn't it? Yes, okay. But it's not negative definite, it's negative semi-definite, isn't it? That's the dilemma. It's not negative definite, it's negative semi-definite. And in this case, actually, we are lucky, actually, we can apply Barbara's lemma. Yeah? That's what it is. So, right. We can apply this, and we know that E actually converges to 0. Time is slowly going. I will see if I want to actually get the proof done, but I've been thinking how to do this. Actually, it's possible. The point is actually we have also a simulation study. And I will upload pretty much actually this kind of thing because I want you to be able, yes, you could do it yourself. I will actually upload it so that you can play with this because actually I have some other plans. But I want you to understand this, and as you see here, in our case, the plan is actually GPB over S plus A. So it's not very much different to what we have seen. We have here A equals -1 and B equals 2. So B, actually the sign of B is 1. Then actually we have here GM being actually our model reference. And yes, and I created then actually this kind actually of simulation where we actually can look here. Well, at first I've been a bit naughty actually. I said actually, okay, I want to be a bit harsher. I created myself a first order system, and well, actually my A parameter, even though it is always actually constant, it's only time obviously piecewise constant. So I just simply actually changed my A parameter over time. I want to make the life a bit more difficult. So this is my A parameter actually, which is fed back actually negatively here into the integrator, and my B parameter actually again changes quite badly, actually between 0.5 and possibly 1.5, yes. And here actually I'm changing between -1 and I think +1 or so. I think that's what I do. So I changed both, yeah, between -1. So I make my plant either stable or unstable. So I switch actually the stability of the plant continuously here. I'm just wanting to have fun and see actually if it works. It's not exactly the task actually given there, but actually I thought, well, maybe let's try that. Now, we have here our reference model. The reference model actually is that one. it's being compared pretty much with the output of our plant. We can observe actually the parameters A and B, and we are feeding actually here the error actually of our y in relation to the reference model into effectively here the into the adaptation for here's y. So effectively that's essentially our AY parameter, and well here is R, so I'm feeding it in there R, so that actually pretty much gives our AR parameter. I'm multiplying here, obviously I'm getting here AR estimated, there's AY estimated, and I need to multiply this with Y and here with R. Yes, am I right here? So I mean the miracles of actually, yes, that's what it is. And then we have here the overall closed loop system. Yeah. So now you possibly understand actually the simulation a bit better before you could see actually this really actually strange actually behavior. And now you possibly appreciate the fact that actually we were having here possibly not so ideal kind of control behavior. So what we have here, we can see our A parameter, which switches actually from from positive to negative. Hence, actually, we are actually creating here actually either a stable or unstable system. The B parameter, I'm not changing the obviously the sign of the B parameter. Yeah, I'm not changing the sign because actually that's what we need to know. If we did that, actually we would mess ourselves up. I mean, yes, then I had to feed in actually pretty much the sign into the adaptive law, which I didn't do actually. I didn't want to change this. And it's possibly plants, I think, are quite ill conditions if actually then their gains are changing. I mean, in chemical plants can actually sometimes behave very strangely. They actually have these local changes actually of input gains. And that can be quite unpleasant. I noticed that at some point. So, and as a result of this, we can see actually here, yes, there is no HUT over there, but that should actually be HUT AR, HUT AY. And as you see, actually, our estimated parameters here, well, they have to change anyway, and dependence actually on these changes here, but even there, actually, they're not staying always constant. The tracking behavior, actually here, the blue is the demand, our AYM, and the yellow is pretty much our plant output. Obviously, it's not always ideal, but one could actually also, well, it's convergence over time towards actually error zero. Yeah? So, well, that's the kind of problem. Obviously, you can't expect that convergence is effectively finite time. There is no finite time convergence. And that's a bit also the dilemma of adaptive control. That adaptive control actually, you don't necessarily get actually time guarantees in adaptive control. And you have also a bit of a problem actually, what happens if I introduce actually a disturbance? That's another issue actually. And these are the typical issues actually in adaptive control. That convergence is not necessarily guaranteed actually. And one of the interesting things actually is, if you want actually convergence to the true parameters, you need something called persistence of excitation. You need to excite your system on a continuous basis. I could have drawn actually possibly the true AR and the true AY, and then we could have tested actually how well it's converging. But in general, actually, it requires so-called persistence of excitation. You can only identify something if you have enough knowledge about it. Yeah? If you don't actually gain enough knowledge about something, you don't know what it is. And that's pretty much the idea of persistence of excitation. You need to actually get information, and to get information, you need to actually change your systems into different kind of situation. You need to persistently excite the system. So I mean, under these conditions, you might be able to get actually the true values of AR and AY. Yeah, so I mean, what I think actually, again, have a look at this. I won't be super fast and putting it up. Actually, I think I will do it more towards the end of the weekend. And, sorry, the end of the week. Possibly the end of the weekend, I think, yes, before. And, yeah, just try to accommodate yourself to this. Barbalas lemma. I can try. Don't throw stones at me. So I changed the lemma a bit. And essentially that's what we need anyway. I changed the assumptions a bit, yeah? F of t is larger or equals 0, yeah? Why do I do this? And, sorry, this is not going to be an exams question, yeah? It's just simply for information. In our case, f of t was essentially e squared of t, yeah? So I think it's quite okay just simply to say actually f of t is larger or equals 0. Then I say actually f of t is smaller than some k. Then I say actually f dot of t. Alright, okay, it's anyway, we don't need this. So f dot of t is smaller than some k. And I mean, k is just large enough to be able to do this. So, have you ever heard of a proof by contradiction? Ever heard of that? Yeah. So effectively, let's assume. So we need to prove that limit of t towards infinity is equals 0, right? And well, let's assume that actually this is not the case. Assumption this is not the case. Right. Okay. So f of t limit is non-equals 0. So let's have a look actually of this f of t, option 1, f of t, actually the limit is t towards infinity equals a constant. Yeah? It's just working through the options. First option is effectively or actually, no, let me think about this. It's not constant, but sorry, f of t remains larger than some constant. It's almost the same. Yeah? What happens in this case? I mean, for actually some t larger than t, it's not, in the beginning it can be, if f of t remains larger than a constant, is actually our integral finite. Not really, isn't it? No. So in this case, the integral f of t is definitely not finite. Okay, cool. So first case is gone. So in principle, there must be obviously some kind of so if we were not converging towards 0, there must be actually infinitely many points. Let's say tk k equals 1, 2, 3, where actually f tk, I mean, if it doesn't stay larger than some constant, actually then for these f tk's actually we are 0 at least. Yeah? But then actually there must be, so that's the first one, but there must be then also others, because we are not converging towards 0, we are assuming we are not converging towards 0. There must be also, let's say, some t I equals 1, 2, and yes, I mean, sorry, and our tk, the limit of tk's k towards infinity, our tk is also infinity. So actually, it's an infinite actually sequence actually of values where we say actually there's an infinite number actually of points where actually our f actually is 0, but then at certain other points actually our f of t I has to be larger than some value c. So what it happens actually, we have our f of t, there must be actually points over time where we are larger and then where we are 0. Okay? So there is possibly a c here, we are larger, and we're then c, and then we are 0 again. Okay? So this must be some interval actually of, if you're saying f of t is not actually converging to 0, actually then we, at some point we need to be larger, and some point we need to be smaller. Because we're not converging to 0. That's what it is. So we're saying we're not converging to 0. So the interesting thing is now that our derivative here, there, is limited. Yeah? So it's always limited, actually, that derivative. So actually, the ability to rise actually from a 0 point to that point is always on a limited gradient. Yeah? Okay? I know it's very mathematical, but I just forget it. So the ability to rise actually up here, the gradient is obviously given by obviously is pretty much given by our limit k, isn't it? And now we have actually infinitely many of these abilities to rise up and rise down. Okay? And there's obviously some value c. Okay, good. So, but we have here obviously some value, actually we are always larger than some value c, because we are not converging actually towards 0. So, I mean, the area under actually here going up and down, under this here, there, is finite, isn't it? So this is a finite area, there is a finite area, there is a finite area, but we have infinitely many of these. Yeah? So meaning actually the integral